Welcome back, ladies and gentlemen. Today we're going to tackle 6.7 similarity transformations, otherwise known as dilations. Up on the screen, you'll see the question, as always, that I'm going to ask you in your exit quiz. Kind of a complicated, longer one this time, but you can totally handle it. To start off, we're going to start with a little vocab. Actually, a lot of vocab. There's a lot of vocab and a lot of notation to go along with this, and your Chapter 6 note guide has many spaces for the information that I'm about to show you. So our first vocab word is dilation, and it means a little something different in English than it does in math. Usually in English, when we say something like your eyes are dilated, that means that your pupils are really big. And it typically only refers to in English as stuff getting bigger. Well, in math, a dilation can apply to things getting both larger and smaller. So a dilation in math means it can be bigger or smaller. And that means that there's two types of dilations, and one where things get bigger and one where things get smaller, and we call them enlargements and reductions. And that's the way it is. The next vocab word you have is the center of dilation. And off to the corner, you'll see a little picture, and you can see if you have the original image right here, and it underwent some sort of dilation, it shrunk a little bit, it got a little bit smaller. You can see that if you draw a ray through the corresponding vertices of the shape, they will intersect at a concurrent point, and that concurrent point is called the center of dilation. Now, I think every time we asked you to do a dilation in this course, I think the dilation center of dilation is 0, 0. So I'm going to say bold statement and say usually it's 0, 0. It's not always 0, 0, but it's usually 0, 0. If you ever run across a dilation that you have to do where the center of dilation is not 0, 0, you basically translate the original shape so that at least one of its vertices is on 0, 0 or on the center of dilation, and then just treat it as if that center of dilation were 0, 0, and figure out how far it is from the center of dilation to each vertex, and then multiply it by the scale factor, which we'll get to in just a moment. In fact, that moment is coming up right now. A scale factor tells you basically how much bigger or how much smaller you want the image to be than the original. And that is, of course, written as a ratio, as this whole chapter is about ratios. And a scale factor is always written in this order from the image to the original. So image comes first or image comes on top uh, when you're writing your scale factor ratios. So you can write it as a ratio or you can write it as a fraction. It doesn't matter. I think most people find it most helpful as a fraction because you will be actually using this number to multiply against your coordinates. So if you treat it as a fraction, you just have it in your head as a fraction and you can treat it as a number as it can be. Um, like a lot of things in math, like the origin has the variable O often ascribed to it. Uh, a scale factor often has the letter K ascribed to it. So just like y equals mx plus b, m is slope, b is y-intercept. Well, k is kind of reserved sort of for any sort of scale factor or some number that's being multiplied by stuff. So k is usually used as a scale factor. That's almost always the variable that we use. Now, if you want to take a coordinate and find its image using a scale factor, there's some notation that goes along with that, and it actually describes to you, if you know how to read it, exactly what to do, how to get the image from the original. And this is what the notation looks like. It says, take your original point and multiply the x coordinate times your scale factor and multiply the original y coordinate times your scale factor, and boom, you're going to get your image. No problem. Done. Now, like I said, k, the scale factor, will affect whether the image is getting larger or getting smaller. And there is a breakpoint for that that you need to be aware of. It's not 0, so it's not like if k is negative, it'll get smaller, and if k is positive, it'll get bigger. The breakpoint is at 1. So you can imagine if you took the original points and you multiplied it by 1, you would just get your original points back out, so nothing would happen. But if you chose something larger than 1, like 10, your image would be, or all the lengths in your image would be 10 times larger. Whereas if you chose something between 0 and 1, it would make it much smaller. And I might just have time to talk about what happens when k is negative today. Okay, there's one more little piece of information, and that is to have to do with notation again. And let's say I have a point A, and it undergoes some sort of transformation. Now remember, transformation is the generic term for anything that you do to a shape. You can slide it, you can flip it, you can rotate it, and today we're talking about dilations. So um, translations, rotations, reflections, and dilations would be the formal terms for it, but slide, flip, I suppose a rotation would be called a turn, and dilations are usually referred to as stretch and shrinks. So if I take A and I transform it in some way and I get an image out of that, we have a little notation that says, hey, I've got an image, and it's called A prime. That's read A prime, and it's just A with a little apostrophe or a dash or whatever it is up in the upper right-hand corner, kind of like a superscript. It's basically an apostrophe. Another thing to know, I don't know if you're going to do too many compound transformations where you take something, transform it, and then transform it again. But if you do take one point and then transform it again under a second transformation, to signify that you're now talking about the very final image, it becomes a double prime. And if you do a third one, it's a triple prime, and on it goes. However, I will say that occasionally uh, the people who write math problems will say turn triangle ABC, transform it into triangle DEF. So they completely change all the variables and they don't deal with the prime notation. But I'm going to use the prime notation because I think it's the most linear in nature. Here's our first example today. It's a very short one, and there's a reason I'm not drawing it, and you'll see that in just a moment. But here's the problem. See if you can pause the video and go right at it. I think it's a pretty easy problem. You should be able to figure out the new coordinates of the new points and use proper notation to do it. Okay, well basically this rule says take the original point, these are our original points here, it's going to be some sort of quadrilateral, and take the x coordinate, multiply it by 3, take the y coordinate and multiply it by 3, and give me a new point. So that new point is going to be called a prime, b prime, c prime, d prime, and all we have to do is take our old coordinate, our original coordinate, 3, and multiply it by 3, so I get 9, and 0 times 3, which is 0. So you get the point 9, 0. If you do that with point B, you get 3, 3, and C, 0, 6, and D, you get 12, 15. So that ends up being a pretty simple problem. I also want you to recognize that you might have to be able to reverse engineer one of these problems. So they won't give you the rule. They'll give you the coordinates of the original and they'll give you the coordinates of the image. And your job will be to come up with the scale factor or to write this line of notation that describes the dilation. So be prepared for that. Okay, we're going to skip over to Geometer's Sketchpad here, and you can see that I've got a seemingly complicated drawing going on here. I was going to be bold and do a quadrilateral, 4 sides, which means that I have to keep track of 8 coordinates, and each coordinate has an x and a y coordinate to go along with it. So all the x and y coordinates uh, or the x and y values for the original shape as we described in our example are right here, and all the x and y coordinates for the image are right here. And you can see that they're slightly off, but you can see right here I have my scale factor set to 1 right now, which means that take all the original points, multiply them by 1, and then get your image points. So all the original points are basically the same thing as the image points except a few of them are off by 1/100th, and I can't get it any closer than that, so we're just going to deal with it. But anyway, basically what that means is that the two shapes are lying right on top of each other. Now, down here I've got a slide bar that controls the scale factor on the x and the y coordinate. So if I take this scale factor and I crank it up a notch, you can see that the shape immediately starts growing. So it basically applies the scale factor immediately to it, and say right now, I'll back that off a little bit. We'll make it a scale factor of 2 because that's a lot easier to multiply in our heads real quickly. But you can see just by visually speaking this length is now twice as long as that length. And if you look at the x coordinate for D and the x coordinate for D prime, you take 4 times 2, you get 8, or roughly 8. 0 times 2 and you still get 0. 1 times 2 and you get 2. 3 times 2 and you get 6. So this scale factor, all it's doing is taking those coordinates and multiplying it by the scale factor. Now the other thing I've got going on here that I wanted to show you is that you don't have to apply the same scale factor to the x coordinates as you do to the y coordinates. So you can take the x coordinates and multiply it by a different scale factor than the y coordinates. And if I do that, you can see that I can stretch and shrink the shape horizontally. And if you notice that the k goes negative, it reflects the shape over the y-axis. And if I stretch it out the other way, I can stretch it out like that. Likewise, I can take the y coordinate or the y scale factor and stretch and shrink it accordingly as well. And this time it reflects over the x-axis. So if I line them up again to be perfect, like each other again, and then shift the whole thing negative, you can see that I can stretch and shrink everything proportionally. Now if I keep doing that, and I shrink it, and I shrink it, and I shrink it, so now notice that the k values are less than 1. They're between 0 and 1. But then if I go negative, something weird happens. So I shrink and I shrink and I shrink, and all of a sudden I'm at the origin, and then boom, it pops out the other side. And you'll notice that shape, if I pause right here, is now reflected over kind of a diagonal line, or you could say that it has been rotated 180 degrees, and the scale factor is 0.5. So it's half as big and it's been rotated 180 degrees by doing that. And that's, I think, all I want to show you on our scale factors today. That's all I have for you this time. I'll see you next time.